So for the second part of this, we're going to talk about molecular orbitals. So this is going to be one video that talks about 9.7 and 9.8. Okay, so molecular orbitals, or molecular orbital theory, otherwise known as MOT. So we want to talk about how did the orbitals combine to create bonds, as well as interacting with one another. So if we think back to the previous section, we talked about a sigma bond overlap, and we talked about a pi bond overlap. But this theory combines wave functions of different electrons to form bonds, or what's going to be called an antibond, okay? So if we really think about this, the question becomes, how are we actually making bonds, and what gives rise to the overlap? Okay, so we have two types of bonds. These are different than the sigma and pi bonds, okay? So in a bonding interaction, so maybe a better word to use here would be types of interactions for bonds, okay? So we have a bonding. This forms a bond, and there is electron density or significant electron density between the two nuclei. This is going to be a lot like a sigma bond, okay? However, if we think about waves, and we know that electrons behave as a wave, we have both positive and negative overlap. So we can also have what's called an anti-bonding. And this says there's no electron density between the two nuclei. Okay, the trick with this is to remember that that doesn't mean that it is a pi bond, right? So the pi bond has no electron density between the two nuclei. It's above and below. So in this case, the anti-bonding, we have electron density that is not between the two nuclei. So these are often called, if we're thinking about a sigma bond, this is going to be called the sigma star bond. Except it's not really a bond because it's anti-bonding, okay? So what does that really mean? Now, if we think about waves, you can add waves together and have positive interference or negative interference. So in this case, the two 1s orbitals, so we're going to make an H2 molecule. So we're going to add together the two 1s orbitals, and you can see this is the sigma 1s. So this is our bonding interaction. This is anti-bonding. Okay. So we have a positive overlap and a negative overlap. These, you can see there's a nodal plane between the two nuclei. So this is the destructive combination. This is positive interaction, okay? So you could imagine that even thus far, even knowing that you have positive interaction and negative interaction, that doesn't necessarily tell you anything about how these two atoms interact with one another. Okay. So molecular orbital theory combines the electrons or the electron interactions that we know exist. So if we think about, and I'm going to go back up to here in a second, we know that we have the 1s, the 2s, the 2p, the 3s, and the 3p, okay? So we have these orbitals, and so when we've talked about making interactions with these, we've often talked about how you have to have two electrons that come together to create a bond. Okay, but the question is, how do you put them together if they're just two p's or sps or something similar? So what we can create are these molecular orbitals, okay? So if these are our two 1s orbitals, we actually can see positive interactions and negative interactions. So in order to create this, you take the 1s, the two 1s orbitals. Both of these have one electron in them, okay? So this is your sigma 1s, and this is the sigma star 1s, okay? So this is going to be our bonding. This is going to be our anti-bonding. Okay. So once we have our two electrons, when we add them together, it turns out what you do is you just, ooh, another color. We're going to fill them both into this. Now, don't forget your molecular orbital or your ability to fill electrons, right? So if we think about this, you take your number of electrons and you fill up. When you get to the 2p, if they're degenerate, you put one electron in each. The same rules still apply, Hund's rules, the Pauli exclusion principle, all of the like. So we take our two 1 electrons and they both add into the sigma 1 star. Okay, so if you have a molecular orbital theory diagram for each of the elements, so this is hydrogen, this is also hydrogen, you fill in their atomic orbitals, and then in the middle we have molecular orbitals, okay? So this is a different drawing where we see that we have the H2 molecule, this forms, so we have a stable molecule. If we look at the helium atom, as we fill them up, right, so we know that helium, so this is helium, it exists as an atomic, right? So it's not a diatomic. If we think about creating the diatomic of He, which we all know based on the periodic table doesn't exist. But why doesn't it exist, okay? Because we could fill these same orbitals up. And so in this case, if you fill up the 1s, the sigma 1s and the sigma 1s star, what does it mean to have both the bonding and the anti-bonding filled? Well, we're going to calculate something called bond order. Let's see if this works. Can you see both of those? Yeah. Oh, no. We'll come back to the second one. Okay. So to calculate bonding, it's half of the bonding electrons minus all of the anti-bonding electrons. Okay, that makes sense. So let's go back to our image before. So if we calculate bonding, it equals 1/2 of, for hydrogen, there are 2 bonding electrons, minus 0 bonds here. I'm going to put these in brackets. So it's half of 2, so we have a bond order of 1. That is a sigma, it's a sigma bond. And so we have a real bond created here. But what about over here? So in this case, we have the bond order. So it equals half of the 2 bonding electrons minus 2 of the anti-bonding electrons. So the bond order here, 1/2 multiplied by 0 is 0. If you do not have a bond order, you do not have a bond, right? So the constructive interactions here leads to a bond. The constructive added together with the destructive leads to a non-bonding event. Okay, so if we think about the helium-2 plus, we've created our atomic orbitals, but so we have 1 here and 1 here. So if we want to calculate the bond order, it is 1/2 of 2 minus 1. So we get a bond order of 0.5. It's not necessarily a real bond, but it does suggest that a helium-2 plus ion could exist. It's not as stable as hydrogen-2, where we have a full bond between both. Before we do this, let's look at our molecular orbital page. Okay. So bonding orbitals have positive overlap. And we have anti-bonding here. For any of these, so I'll do this one for you, right? Remember, so these are our atomic orbitals. These are our molecular orbitals. We have a hydrogen on each side. As we add in their electrons, they each have 1 electron in the 1s. And then we can go back, oops, wrong color, and put the 2 electrons in here. Okay, so we can calculate the bond order, which is half of the bonding minus all of the anti-bonding. Now, we did this a little while ago, so you can go back and recalculate them using your diagrams. But let's talk about these 2 words, because a lot of times when we talk about molecular orbital theory, we actually talk about these, and we think about them in ways, particularly when we get to things like semiconductors and more complex ions. So the HOMO is the highest occupied molecular orbital. And the LUMO is the lowest unoccupied molecular orbital. Okay, and so we often ask the question of how many electrons are in the HOMO or how many electrons are in the LUMO. So you can look back at both of those. The other thing we can often do with molecular orbitals is to write out the electron configuration. So for hydrogen, if we were to write it out the normal way, right, it's 1s1. That just tells you where it is. But you can write out the electron configurations for the MOs, right? So the molecular orbitals here allow you to combine this. So in this case, we have the sigma 1s2, okay? So this is the electron configuration here. If if we were to write it out for helium, it's the sigma 1s2, sigma star, the 1s sigma star 2, okay? So you can also calculate the bond order from here without having to draw the molecular orbital, because you can still subtract, take half of the bonding minus the anti-bonding. So you would sum up all of the positive interactions and delete all of the negative interactions. Okay, last section. So for the period 2 diatomics, let's get something a little bit more complicated happening. So we can predict the orbital mixing using MO theory. Okay, so as always, when we talk about orbitals, we have a handful of rules. The number of molecular orbitals is formed from the same number of atomic orbitals. This makes sense, right? So when we created hybrid orbitals, the number of orbitals that went in is the same number of atomic orbitals, okay? Atomic orbitals combine most effective with atomic orbitals of similar energy. So if we want to combine an atom, we need similar orbitals to interact with one another. As orbital overlap increases, the energy of the bonding MO decreases and the antibonding increases, okay? Each MO, like any other orbital, can only accommodate 2 electrons. And we follow Hund's rule. Fill 1 electron in each degenerate orbital first, and lowest energy is filled first. Okay, so for lithium, so you can work along with me in your handout. I'll do it on the handout as we go. Okay, so the first things first, for lithium-2, we have our 2 lithium atoms on either side. In this case, we are going to fill the atomic orbitals first. So we have 3 electrons in each. Okay. So in this case, we want to combine. So we take 1 electron from either side and put it into the MOs. 2. So we now have 3 orbitals that are fully filled. And we could calculate the bond order. It's equal to half of 4 minus 2. So we end up with a bond order of 1. This tells you that you can have this molecule, okay? So we can create this. So thus far, we've only talked about s orbital overlap. If we were to look back just to remind ourselves, this is what we see. We see positive overlap and negative overlap. We just have bonding and anti-bonding. But what happens when we get to the p orbitals? Because they're always so much more complicated. Okay, so we can have orientation of the p orbitals, which we know they're all 90 degrees apart. So we can have end-on overlap. So this creates internuclear. So this is going to be a sigma bond. Okay, when we have sideways overlap, whether it is in the plane of the paper or above and below, this creates pi bonds. So the names of these are the sigma 2p, the sigma star 2p, the pi star 2p, pi 2p. There are just multiple 2p pi's. So we have 2 of these. Okay, and so the multiple pi 2p's is how you can give rise to a triple bond. Okay, so it turns out that there are different types of orbital mixing and orbital splitting. So we can now create a new molecular orbital diagram. So previously we only used the 1s and the 2s. In this case, the 1s is missing, but it would look just like the 2s, a little bit lower in energy. So for any atom, we could create this diagram. Although it turns out for the period 2 diatomics, there's a little bit of confusion as to the, not confusion, the orbital overlaps, whether you fill the pi 2p or the sigma 2p first or second. So as you have increasing sigma 2s and sigma 2p interaction, it causes the energy splitting to change. So what does that mean? For oxygen, fluorine, and neon, we have this molecular arrangement, okay? For boron, carbon, and nitrogen, we see this interaction. This has a large 2s, 2p interaction. This has a small 2s, 2p interaction, okay? These are probably larger because they're going to be closer together. These will be larger. This is smaller because they are further apart. So there's this diagram. So in this case, the atomic orbitals are missing. We are just showing these. Okay. So in this graph, we can see that there are different arrangements. So here are all of the sigma 1s and or the 2s and the sigma stars. So if we move up into the sigma 2p's or the pi 2p's. So for boron 2, we would say a positive bond order of 1, which is good, and it's paramagnetic. So in this case, we also see for a carbon-carbon bond, we would have 2 pi 2p orbitals. You can see that we start to see different types of orbitals as we go up. But you'll note that you can predict paramagnetics or diamagnetics. What does that mean? A paramagnetic, we have 2 unpaired electrons in the highest occupied orbital, or the HOMO, right? How many electrons are in the LUMOS? 0, because it's the lowest unoccupied orbital. So there are never electrons in the LUMO. Oh, we don't need that. Okay, let's look at our handout real fast. So if you were provided this, or the corresponding small 2p interaction, right? So these, you could go back and fill them in for any of these atoms and calculate the bond order. So let's just, you can do that. Oops, sorry. So here is the small 2s 2p. But let's think about heterodiatomics. A heterodiatomic is when we have 2 unequal elements. So we could have carbon monoxide, we could have NO. So, but if we look at their molecular orbital theory, because now we can actually talk about their electrons. So how does this work? If you have the nitrogen and you have the oxygen, you would draw both of them on the side. Let's work with this here. Okay. So we have nitrogen and oxygen, and we see their atomic orbitals. They're slightly different in energy, but that's totally okay. But how can we work with this? So we can fill the nitrogen. So there are 5 electrons in the valence, and oxygen has 6. Okay, so we have these electrons. Now we can fill the molecular orbitals. So we're going to fill both of these. Now, we donate 1 electron from either side. 1, 2, 3, 4. So we started with, okay. So as we filled them up, we can now calculate the bond order. Okay, so if it's half of the bonding electrons over 1, 2, 3, 4, 5, 6, 7, 8, minus 1, 2, 3. So we end up with 5 halves, or 2.5. So this is new and different, right? So we end up having a sigma and 2 pi bonds. But if we think about NO, there's often an unpaired electron. This is where that unpaired electron goes. It alters the bonding just slightly, not a whole lot, just a little bit. Okay, so for any diatomic, you can fill them out, and you can ask questions like, how many electrons are in the LUMO? How many electrons are in the HOMO? Okay. But we can do any of these. And so you could also ask yourself about carbon monoxide. So if carbon has 4 electrons, so we can start to fill them up. So you could imagine that we would have something that looks like this, I think. Yeah, there will be some formal charges associated with this. But you, for all of these, can write out this and calculate the bond order. With that, that's it. So happy Thanksgiving. Don't forget to take the quiz. The answer to number 10 is yes. It asks if you had a great Thanksgiving. See you guys next week.